Hello and welcome. We're going to continue our discussion now and start talking about statistical geometry. And we started last time by talking about statistics in general, and I gave you an introduction to statistics. And now we're going to apply some of those different distributions and things that we learned here. And we're going to start out actually a little bit far away from what sounds like paper making, but we're going to bring it back into paper making and paper physics. And so I'm going to start off by conducting sort of just a simple thought experiment. Okay, so for this thought experiment, we can imagine a field or a sidewalk or something of that nature, and we're going to break this area up into grids. And so in this particular situation, we have 9 total areas. Now, falling down onto these 9 different areas, we are going to have raindrops. So let's say we have a bunch of raindrops that fall down to these individual dots that kind of fall down randomly on top of this. Now we're going to assume that these dots, once they fall down, or these raindrops, once they fall into this area, either fall in a particular square or outside a particular square. They don't fall on the line, they have to fall either in or out of that square, so they can't fall on either one of those. So you have these raindrops falling down all over the place. Okay? So the raindrops are falling down, and we might want to know something like how many raindrops on average fall in a single square. So let's just take this a little bit further. So let's start with a 100 meter squared area. $10,000 raindrops fall. Can you answer the following? So the first question: what are the average number of raindrops that fall per meter squared? Okay, so how would we determine this? If they randomly fall, we'd know that a total of 10,000 raindrops fell over a 100 square meter area. So if we have 10,000 raindrops and we divide that by 100 meters squared, we would find out that on average 100 raindrops fall per meter squared. So on average we have 100 raindrops per meter squared. Now the next thing I would like you to answer is, what is the standard deviation in the number of raindrops that fall per meter squared? So we know the average, now we'd like to know the standard deviation. So this is a little bit more challenging. It was kind of straightforward to calculate the average. But now to calculate the standard deviation, we have to take something else into consideration. And the first thing we have to take into consideration is, what is the distribution of data? What might that distribution of data look like for the number of raindrops that fell? And we could think of a lot of different distributions, But one that is quite convenient for us and that we talked about is the Poisson's distribution that handles non-negative integer values. And we talked about this before, that raindrops either fall in an area or out of an area, not on the edge of an area. So they're either in the area or out of the area, so they have a discrete positive integer value. So this is probably a good choice. So let's just assume that the Poisson distribution applies. So if the Poisson distribution applies, we know something about the Poisson's distribution. We know that sigma squared is equal to mu. So sigma squared is equal to the mean value, and that would mean the standard deviation, so the variance is equal to the mean value, that the standard deviation is equal to the square root of the mean value. This is from the definition of the Poisson's distribution. We know these facts. Well, seeing how as we know mu from up here, right, this is equal to mu, we can easily calculate sigma is equal to the square root of mu, which is equal to the square root of 100. Now, this is an important point. The units are different on this because the units of standard deviation and mean are the same, but the units of variance and mean are not the same. So numerically these numbers are the same. The actual units on this would be raindrops squared meters to the fourth. And once we take the standard deviation of that, our standard deviation would be 10 raindrops per meter squared would be the standard deviation on that particular area. Okay? So again, this is pretty straightforward. We've gone through this now. Using the definition and assuming the Poisson's distribution applies, we can calculate the mean and the standard deviation. Pretty easy. Now, number 3. What is the probability that 0, 10, 100, and 200 raindrops fall in 1 meter squared? Again, let's use the Poisson's distribution here. So we'll assume that the Poisson's distribution applies, and if we do that, we can simply put this into the Poisson's distribution. So the Poisson distribution is probability of x with lambda is equal to e to the minus lambda, lambda raised to the x over x factorial. And this is for values, integer values, positive integer values, which all these numbers are up above. So applying what we have, we know that lambda is our mean, which is equal to mu, which is equal to 100. And our x's are going to take these different values. So we end up with p of x slash 100 is equal to e to the minus 100, 100 raised to the x over x factorial. And now putting these into our calculations, I can show you just the easiest one here. When x equals to 0, I have e to the minus 100, 100 raised to 0 over 0 factorial. You should recall that by definition 0 factorial is equal to 1. So what do we end up with? For this particular probability, the probability of 0, 100 is e to the minus 100. So we would see that the probability of finding 0 raindrops when the average is 100 raindrops per meter squared is e to the minus 100. That's a pretty low probability. If we wanted to calculate it for p is equal to 2, so if we wanted to calculate, 10, so p is equal to 10, again, we're going to put the 100 in, or the 10 in for the x. We'll have e to the minus 100 times 100 raised to the 10th power over 10 factorial. You can do that calculation. If you do this for 100, x equals 100, e to the minus 100, 100 raised to the 100 over 100 factorial. Depends how good your calculator is. You may or may not be able to find that particular value right there. And p is equal to 200, or x is equal to 200, and the probability is e to the minus 100, 100 raised to the 200 over 200 factorial. So when you start plugging these into your calculators, chances are you'll be able to do this one. You may or may not be able to do this one, and in all likelihood this factorial becomes too big for most calculators, although some of the more expensive calculators you might have, that'll actually work in. So now we've been able to calculate some pretty basic things about raindrops falling, and that seems sort of far away from what we're working on in paper physics right now, but we can basically here calculate the number of raindrops that fall within a certain area. We can also determine then what the standard deviation is of those raindrops falling within a certain area. And then finally, we can calculate the probabilities of different likelihoods of the number of raindrops falling within a particular area. Now, we can take this one step further, and we can extend this to a random line network. So a random line network. So let's extend this to a random line network. So we have a random line network, and we'd like to see if we can do some statistics on this random line network. Now, we don't have raindrops falling down. Instead, we're going to have lines, and these lines, we can imagine, are fibers. So these lines have some finite length and maybe even some finite width to them, but these are essentially fibers. They're these straight fibers that we're going to let fall onto an area. And we're going to pick out right here the center of that fiber. Okay, so we're going to look at fiber centers. So that's the center of the fiber. And instead of counting raindrops now, we're going to count the number of fiber centers that fall within a given area. Okay, so this is kind of critical here. So we're going to look at fiber centers. So essentially every raindrop that we had up above now would represent the center of a particular fiber. So for every raindrop that falls, that's essentially representing the center of a fiber falling down. So let's imagine now that we have 10,000 fibers. Falling on a smaller area now. Oops, falling on an area of 10 centimeters by 10 centimeters. So this is just 100 centimeters squared. Answer the questions for above. What will you get? So number one, the average number of fibers falling within a 1 centimeter square area, right? So we've changed from meter squared to centimeter squared now. We would simply say number of fibers per 1 centimeter squared, we would have 100 fibers per centimeter squared. 2. Standard, oh, let me write this out and abbreviate it. Standard deviation of number of fibers per centimeter squared. It's simply the square root of 100 fibers squared, centimeters to the 4th, and that's equal to the standard deviation, or 10 fibers per centimeter squared. And actually, if you look at this for number 3, the numerical results would be identical. So probability of finding the probability of finding 0, 10, 100, and 200 fibers in a centimeter squared. The results numerically would be identical, actually. Okay, so we've just made that transition then. So we made a very simple transition to go from this raindrop experiment over to this fiber experiment falling down. And now we've actually stumbled onto something that's very interesting, because one thing that's very important for us to understand about the structure of fibrous networks is how the mass is distributed over these fibrous networks. So we want to know something about the mass distribution. And that mass distribution is something that we call formation, or the formation of these fibrous networks. And in particular, the formation we can define as the variability in the local basis weight. So in this particular case, we're looking at, if we can imagine holding up a sheet of paper up to the light, you can actually see light areas and dark areas. If we took that sheet of paper and cut it up into some very small areas and measured the basis weight in each one of these different areas, we would like to know the variability in that basis weight. And that's a characterization of the formation of our paper sheet. And that's important for printing properties, for strength properties, and for a lot of other properties. It's a good way to ensure that we have good uniformity in our paper sheet. For other non-woven materials where you may have these similar situations occur, all these same statistics will apply. And now, with what we've just talked about, we know the number of fibers that fall and the standard deviation of those fibers. Right? So we know the mean number of fibers and the standard deviation. This is good, right? This is very good, because this allows us to get an idea of the variability of the basis weight, because we can imagine that the basis weight is proportional to the number of fibers in an area. And we'll begin talking more and more about this as we go on. That's what I'm going to leave you with today, and we'll pick it up next time, making the translation from these small points here over to basis weight and formation of our paper sheet. Thank you.